Welcome to my presentation on differentiable physics, of course, for deep learning. My name is Nils Thuerey from the Technical University of Munich, and I want to talk a bit about the recent research we have been doing in this area, which I think is a very exciting one for a large variety of fields. So let me start motivating this a bit more broadly. So physical effects are really everywhere around us, starting from the air we breathe, the water we drink. Here you can see some examples in motion: smoke, the flow around an airfoil, or also splashing water with surface tension effects in this case. For control, like robots, this is also very important in practice. Here you can see a nice example of a robotic fish. Beyond these, there's a large variety of other effects that obey very similar advection diffusion type laws: thermodynamics, plasma simulations, a lot of medical phenomena. So it's really a large variety of things we can cover here. I will be looking specifically at Navier-Stokes and related effects, but as mentioned before, these advection diffusion type systems with constraints come up in many disciplines. Now, the kind of key or central question in this context is now, we have a lot of powerful methods for forward and inverse problems. How can we combine these with deep learning? So that's going to be the key goal of all of these approaches that I will be talking about. Let me try to put this a bit more on the map of research. In a way, we are targeting the intersection of machine learning, numerical methods, and physical simulation. So the green dot here in the middle. And if we look at that a bit more closely, we have the aforementioned kind of regular forward simulations, meaning I start with a set of initial conditions, I compute, for example, a solution over time. Inverse problems are also crucial for a large variety of cases. So here we actually want to find a set of optimal parameters, boundary conditions, in general parameterization of a certain problem such that certain physical constraints are fulfilled. However, these work together. So I'm targeting both of these problems within the larger area of physical systems here. Now the question is, how can we get that together with deep learning? So if we look at deep learning as another axis here on the side, in a way, a starting point is what I summarize here as supervised approaches, meaning the physical system can provide data and we want to learn some physical function, but in a way this is very loosely coupled. We're really working on the basis of data here. Hence, this box is shifted towards the right. Now, if we integrate this a bit more closely, we can actually incorporate knowledge about the physical system in the loss terms of our learning problem. That's the second approach here, and as you can see, this is a bit more tightly integrated. However, the tightest and closest link between the two that I want to aim at here is actually if we do this in an interleave fashion, meaning we alternate neural network evaluations, physical models, and in a way they tightly play together and influence each other. So that is also one of the key goals actually of this setting of differentiable physics. I also want to at least mention we're not the only ones working in this direction. There's in the recent years really a surge of interest in combining physics and deep learning. Here you can find a few very interesting papers, and at the top these two are actually our works and the ones I'll be focusing on in the following. And at this point I also directly want to acknowledge the very hard work that PhD students and postdocs have invested in this project. Philip and Kiwon especially, but also collaborators Vladlen, Robert, and Raymond. So thanks to all of them for working on these research works that I'll be presenting in the following. Yeah, as a first application, I want to target what we've dubbed learning with a solver in the loop. So what is the idea here? Let me again start with the bigger picture. Here, the overall goal really is to reduce the numerical errors in a simulation. So the blob you can see here in blue on the left side, that is some reference discretization and space of solutions. In this manifold, we have points indicated by the dots here, and a trajectory of these points is one instance of a solution over time. And yeah, these in a way provides our ground truth. This is the data we want to match or aim for. And we now have a coarser discretization of that. You can see the outline here of this blue shape on the right with more edges, meaning it's potentially a lower resolution. It could also be a lower order discretization. And if we now compute purely in this more approximate space, we actually in practice often only get this orange blob, a smaller one in a way, as shown here on the right hand side, meaning we probably cannot fully resolve the space of solutions in this lower resolution, which I'll refer to as source in the following. So this is going to be also the basis that we want to improve. Now, the goal is in a way to augment and improve the errors made by this coarse source simulation with a learned model. So we are always still using the source solver. We're not completely replacing it, but it needs to kind of interact with the learned model. And the goal is to basically get closer towards these reference solutions, at least in a way as they're projected onto this coarser space. And that is actually what this white arrow with the T, the projection operator, indicates here. So we want to reduce the numerical error between this coarse approximation and the reference with the learned model, to summarize. One key challenge here that I directly want to point out in this view is that we are dealing with inputs that change. Hence, we have a shift of the distribution of the features of the inputs. So here's a very low dimensional sketch indicating that source and this reference simulations probably look very different in terms of inputs. You can imagine basically a small neighborhood, for example, of a solution. In practice, these inputs are very high dimensional and these shifts will be non-trivial, but this image indicates a bit, if we imagine we have 1D space, how this might look like. And now the key challenge here is that when we correct the source simulation with our learned model, these inputs will change. The behavior of the dynamics should change. We want to get the reference. And these corrected variants, these modified solutions, they don't exist until we have the model. Hence, we cannot actually pre-compute these. We cannot train a model if we rely on pre-computation with this shifted distribution. So in a way, one of the crucial problems here is how can we actually train a model that really can rely on seeing these modified inputs? Because we can imagine if we only rely on the source but still basically change it and expect the model to retrieve the reference from these inputs it might have never seen at training time, that is probably an extremely difficult or potentially infeasible task. Yeah. To show a first example here, on the left-hand side you can now see in 3D example one of these reference simulations, and on the right-hand side directly you can see the source simulation. In this coarse resolution it cannot actually resolve any of these interesting motions behind the cylinder. And here is now again the reference simulation with a model that now improves the same source simulation as before. And I hope you see that now these simulations are actually very similar. I'll get to more quantified results later on. This is just as a preview of the results you can actually achieve with such a model. Yeah, also some very important information right away at the beginning. So in our paper we actually show these 3D simulations in an image like this. And now I guess it's clear that this paper is actually in reality about fish smoking cigars. But just to point that out here before we get into the details. Yeah, let me explain the notation for the following examples in a bit more detail. So we were given a PDE model, right? For example, fluid flow or a different one, denoted by P in the following, and then we have the solution manifolds for the reference and the source spaces as indicated by these blobs before. Additionally, we have a projection operator, in an easiest case just a downsampling from a high to a low resolution denoted by T in the following, and the simulation or the advancements in time are now computed by repeatedly applying the PDE operator, a discretized version of it. Typically we're starting with a projected reference point at time t, and then n times apply our PDE operator to get a state in the source space at time t plus n. So this is a typical setup that we'll be following. And now we include a learned model here, typically denoted by C in the following, that retrieves one of these source spaces, and then given a set of weights, theta in the following, it now should reduce the L2 distance towards the reference states. And in practice, we compute that over a certain time horizon, so n steps in practice, and that's summarized here at the bottom. So as a simulated state at time t plus a correction for that time step should match the projected reference state at time t plus I plus 1, so the next instance in time, in terms of an L2 norm. Yeah, so one of the really crucial bits to point out here is we now want to train these kind of iterative procedures, the repeated application of this PDE model with differentiable physics by really looking ahead over multiple time steps. And now I want to just visualize that once for a single training iteration. So let's imagine top to bottom we have different iterations of our favorite deep learning optimizer, typically Adam with 10 to the minus 4, but doesn't matter too much what that is. And now at one of these iterations, we're starting with an initial source state. I'm leaving out the mini batch here. Typically that's done for 4 to 8 or so in parallel, of course. And we're applying a correction to the state, then performing a simulation step. And this we are now repeating n minus 1 times to get to the final state. Now, for all of these states, we have the reference. So across the sequence of steps, we can compute a loss, namely the difference towards the reference. And these differences are now backpropagated through the n minus 1 steps of simulation. So we have a differentiable physics solver, hence with an adjoint, we can actually get a gradient flowing through the simulation step. This also then allows us to compute a gradient with respect to the inferred correction by the correction function C here. So we get an update for the weights theta, and we get this for every step along the way. We actually have reference points across the sequence, and we're computing a loss across all these different steps. And this full backward-forward loop is actually really what happens within every update of our learning optimization. And typically also in parallel for several simulations. So it definitely increases the computational effort at training time, but as I'll show later on, it actually pays off significantly in terms of the quality of the functions that the network can actually learn. Yeah, so after this one update step, we can then continue with the next update of the network. Yeah, let me show a first example of in a bit more detail for these error corrections. So a nice setup to look at is an unsteady wake flow in 2D. In this case, as a reference, we're using a 4 times higher simulation, otherwise unmodified. And yeah, we have a domain that's actually 2 times higher than wide, an inflow at the bottom, obstacle of 1/10 at 1/2, 1/2, and a collection of training data with a set of distinct Reynolds numbers. And as test cases, we now choose a set of new Reynolds numbers that were not seen at training time to evaluate how well the model works. Here on the right, you can now see one of these test cases. So that's one that was not seen at training time. At the bottom, you can see this higher resolution reference that nicely resolves the vortices behind the obstacle. And at the top, you can see at this resolution, the source really cannot properly resolve these vortices and gives a very different flow behind the obstacle at the bottom. So we can also measure the kind of base error of the source simulation, in this case 0.146. What you can see now at the top is one of the solver in the loop models interacting with the source simulation. This one was trained for 32 steps, hence the subscript. And as you can see already across the sequence, now this model actually manages to restore the vortex shading very accurately. So this does a lot better than the source simulation, and this also shows up in the resulting error measurements. This is averaged across all test cases now, but it basically reduces the error by more than a factor of 10. So it really gets very close to the ground truth in this case. I directly want to get back to the distribution shift. So this is actually a good example to highlight that again. Here, this is one of the key difficulties. So as mentioned before, it's very difficult to really quantify the whole shift of this high dimensional distribution. In this case, it's the CNN, so across the whole the receptive field of the CNN. But this kind of core distance of 0.146 already indicates that we have a very substantial shift, at least for the mean, and very likely also for all the other modes of the inputs with respect to source and reference solutions. And now, when we change when we apply the corrections, we actually get much closer to the reference, and this is really what the model needs to see at training time in order to properly learn from it. And with these differentiable physics solvers, we can really unroll the different steps, the effectively 31 steps in the previous case, at training time. So the model really sees how these corrections influence the solutions, and it can then learn from these changed inputs that, in this case, are actually quite close to the reference and very different from the source inputs that were pre-computed and used for training. Yeah, I briefly want to mention, if you're interested in all the details, please have a look at the paper. We provide much more detailed evaluations there, but one thing to highlight, we're using different models here for this case, and for example, increasing the number of these unrolling steps at every training iteration significantly brings down the error from 0.041 to the aforementioned 0.013. And I think it's also worth showing these in motion again. So here are a relatively low and high Reynolds number from the test set. And again, the source simulations on the left, you can see it deviates from the reference even for this low Reynolds number. The solver manages to restore it, and likewise for the higher Reynolds number, the difference is even larger, but the learned model really manages to capture the behavior quite closely. In our paper, we actually present a whole range of different test cases. I don't want to go through all of them here, but one other one I briefly want to mention. We're also looking at a buoyancy-driven flow. So here we have a coupled system, a simple temperature model with a Boussinesq approximation, and as you can see here, also very different behavior for source and reference, and in the middle, the learned solution again captures a lot of that behavior. Now, it's a coupled system without explicitly solving for viscosity in this case, but with a buoyancy term from a density quantity d here. And what's worth mentioning in this case, for this setup, we actually used a kind of black box solver for the reference trajectories. In this case, we're using a higher order pressure solve. Note that this one does not have to be differentiable. In a way, this is really just external reference data. We rely on differentiable source solver. The references could potentially come from another system. Yeah, so here it's also nice to look at the progression of different unrolling steps at training time. So in this case, here in this graph now, I also can show the result for a kind of regular supervised version without any differentiable physics. It actually does not do too badly. You can reduce the error also to some extent with that. In this case by 29%, here denoted by none. However, right, putting the solver into the loop really pays off very consistently. And for 4 steps, we're already at 41%. And then all the way towards the right, you can actually see a model with 128 steps that reduces the error for this buoyancy case by 60%. And it's a nice progression. We only evaluated up to 128 steps. Potentially, there are even larger payoffs for more steps. Yeah, and also to give a bit more specifics here for the 3D case. So this is actually similar to the example I showed in the beginning. Now for Reynolds number 486. And the 3D case is interesting because it is on the one hand a lot more complex. We now have the 3-dimensional rotations. And if we train a model in a fully supervised fashion, this non-model here on the left, this actually fails to produce stable simulations. At some point, for pretty much all of the test cases, it starts to deviate, most likely due to the distribution shift, basically gets confused and pushes the flow in wrong directions. On the right, the solver in the loop model stays close to the reference. So here you can actually now also see the reference on the side here, and the solver actually keeps the model stable and manages to recreate the complex behavior of the reference simulation. Yeah. Oh. Let me continue. One last comment about this case. The performance. Potentially, we can, of course, resolve these accurate simulations by investing compute time. Here, for the 3D case, a CPU-based reference simulation would actually take more than 900 seconds, while the learned version, so evaluating both the correction and the solver on the lower resolution, also 4 times lower in this case, on a GPU require only 13.3 seconds. So it's a large factor, 68 in this case. Of course, there's also a difference between GPU and CPU, and it depends a lot on implementation specifics. Also, admittedly, our version is not yet that optimized. But I think this indicates a bit that we could see huge speedups here, and I think this is really just the tip of the iceberg, if you want. What's already the case with this model is that it's in a way a pre-trained corrector. Even if we don't change it, I think that we will see very substantial speedups in the future, just because the support for evaluating neural networks is really gaining a lot in terms of performance from upcoming hardware generations, while a lot of the CPU performance stagnates at the moment. So I think also potentially for other solvers, there's really a lot to be gained from this combination, from these hybrid solvers using kind of a coarse approximation and a learned corrector. Yeah, with that, let me come to another topic, namely that of control. Oh, sorry. So here we are looking at a different paper now. This is the second application that I want to discuss in this talk. And the setup is a slightly different one, although the approach uses very similar concepts. So one scenario that we can imagine here is, let's imagine we have a floor plan or a room, and a fire breaks out, emergency, and we have a ventilation system that we want to control such that the smoke from the fire is driven out of the building or the room as quickly as possible. So we can control certain vents at the top, for example. And now how do we need to set these in order to get the flow in the right direction? This is a control problem that involves the flow of the gas in this room, and ideally should also be evaluated quickly. So these kinds of control settings are what we'll look at next. And naturally they also involve the time dimension, right? So we cannot expect to immediately get the smoke out, but we might aim for it in a certain time span to transport the smoke into one of the exhaust areas. So the overall concept and loop is quite similar. We again have certain learning steps, and in every learning step we are unrolling the temporal evolution of the problem. Now instead of this corrector, we have what we called a CFE network, a control force estimator, that now not only takes a current state, so this is one of the key differences here, but it has to aim for a longer term target. So in a way, the goal of this network is a bit less immediate. Hence, it also receives a velocity u here, the target to reach, and also the time span when to reach it. And if we imagine that the target should actually be reached after the sequence of n steps, one of the main differences here is that we also evaluate the loss at this very last point. So after the n steps, we don't have losses in between, and then we need to backpropagate the signal from this final point through the sequence all the way until the earlier steps and through these different invocations of the CFE network. And again, these passes are done for every one of the learning steps. Another change for the control task is that we noticed this CFE network with its kind of local action only has limited chance to arrive at this goal. We need something that thinks ahead and plans a bit. And this is where a second network now comes into play. So we're training two in this case. That's a prediction network. So we have one network that actually, in a way, imagines what should happen at a certain time horizon. That's the plan. And then this CFE network, that's the one that actually does the action, that pushes the flow in a certain direction or so. So that acts locally between time steps, and the predictor, that one is actually in practice trained for different horizons. Again, we have different networks for kind of specialized for different time horizons, and then the corrector can act on these. Yeah, I don't have time to go into all the details, but we actually have an efficient kind of hierarchical scheme to address that. So that reduces the complexity and the number of executions of the predictor. Yeah, so one toy example to look at here to make this a bit more clear what happens in the whole domain is a Burger's advection diffusion case. It's already nonlinear, but only a 1D case. And here on the left, well, let me go back, you can actually see the unmodified simulation. So we have in cyan, in the dashed line, we have the initial state. And in this case, it actually contracts towards the purple curve in the middle, receiving an unknown set of forces throughout this trajectory of 32 steps, I believe, in this case. Now we can train the CFE network and drive the evolution towards the target, and it actually learns to recover a lot of these unknown forces. But as you can see here, the solution is actually jittering quite a bit. It deviates from the reference, and yeah, it's actually not very smooth and also not optimal in terms of the applied forces. If we now bring the differentiable physics into play, again unrolling the sequence of different steps, we can see that we get something that actually fits the reference much more closely. And again, one slight difference that I just want to mention here in this talk is if we kind of re-evaluate the predictor as a refinement, as we call it, this further improves the quality of the solutions at a smaller scale, as you can see in the images on the right. Yeah, now to come back to the fire example from the beginning, I wouldn't have mentioned that case if we wouldn't have targeted it in our paper. So we simulated this room or this floor plan here with the white walls shown in the images. Now the model can only influence the outer region of this two-dimensional Navier-Stokes flow. It's actually also 128 squared. The velocity errors you see here are only subset. And now the goal is to basically bring the smoke in yellow into one of the windows at the top of the domain indicated by the arrows. And as you can see in these three examples, the network actually manages to indirectly control the flow over the whole sequence and transport the flow in the right window target region. And this is actually not trained, right, also in terms of control for the whole time span of the simulation. Again, for a more detailed evaluation and more quantified results, please check out the paper to show some aspects of this. Here is a graph that compares the force magnitudes from differently trained models. And of course, in a way, we want to apply as little forces as possible. It's trivial if we just brute force push the solution into the final state, but we want a network that actually understands the physics and minimizes the force needed. And there are very substantial changes with respect to these forces. So the regular CFE chain actually needs almost more than 83 units of forces. Using differentiable physics for the force estimator already reduces this to 28. And then with the whole refined prediction scheme, we can actually half that again to around 14, shown here in blue in the histogram in the graph. So it clearly has the least and the smallest forces being applied over the course of these simulations. Yeah, so that also indicates again how important it is to actually let the network learn from the physical evolution at training time. And for these control problems, one of the questions we actually got a few times was, well, if you have a gradient, why don't you just optimize for it, right? So if we have this target transporting the smoke somewhere, we have the gradients, why not just do gradient descent on such a force field to get the answer? And you can do that, of course. So on the left here, you can see an example of that in a moment. However, if we just do it naively, follow the gradient, actually very quickly get stuck. This does not work very well. So what you see here is already a hierarchical scheme with some tricks to actually make this converge. And as you can see in this solution, the goal is to actually transport the initial blob into this rectangle closer to the top. It gets there. However, it follows an unintuitive path. It's divergent free and adheres to Navier-Stokes, of course, but it takes this S-curve and required 1,500 steps, took around 130 seconds in total. The solution inferred by our network, as you can see here on the right-hand side, now looks the same. Unfortunately, it seems the export of the presentation gave the wrong video here. So sorry for that. The learned solution is actually inferred much faster. And if you check out the examples we have in the paper, it actually also follows a much more intuitive trajectory. Please check out the original results here. This is 2 times the result from the regular optimization. Yeah, that also concludes the discussion of different applications in the context of differentiable physics. And I briefly want to summarize these results again. So I hope I was able to show a bit that using differentiable physics in combination with deep learning is really a very powerful tool that can give much better results than supervised or only loss-based variants. So for example, the first application I discussed, it can actually learn regular patterns in these errors of numerical methods and very significantly reduce the numerical errors. And also, if we combine it or employ it in a control setting, it can actually learn to anticipate the long-term behavior of a simulation and control it in a way that very efficiently minimizes the applied forces. Let me discuss a bit also now what happened here, what have we seen. So all of these learning tasks in a way navigate a very complicated energy landscape. So let's imagine this scenario here, that's our energy landscape. We're starting at where the flag is here at the bottom. And now we want to minimize, find a minimum here. Maybe that's the green flag in the distance here. And of course, it's completely dark. We have no clue where we're going because in these optimization problems, we don't have a global view. We are just starting somewhere, and from there, we need to find the target state. Now, in a supervised setting, that basically means we are kind of randomly sampling this landscape, checking out, well, what's the elevation here. And then in practice, training with the supervised setup typically gives us something like a geometric mean, which might actually be very far from the optimum that we want to reach. An interesting alternative in the setting that is also very powerful in many applications is reinforcement learning, which now kind of re-evaluates an environment, as typically called there. In this case, that would be our physics simulation on the fly, and tries to find its way towards this target point, but in a way that's also walking around in the dark here, and in practice is actually very difficult to make converge and often also requires a lot of evaluation steps. With the differentiable physics, however, the key difference in a way is that now for the evaluations of the physical system, we're getting directions. So potentially we can actually find a minimum with fewer steps following the gradient information at optimization time. And also, I didn't have time to discuss it in more detail, but it's actually not so easy to purely learn from differentiable physics in practice. We highly recommend combining supervised approaches for kind of initialization step for stabilization with the differentiable physics losses. But as indicated a bit by these results here, this really very clearly outperforms supervised results and typically also gives results much faster than the exploration of a reinforcement learning setup. Yeah, one interesting future direction that I think is really exciting is to apply this concept to real-world flows. I've purely shown synthetic data here. However, one area that we are also looking at right now is we have a multi-camera setup that captures a fog from a fog machine here. As you can see in this video, we can reconstruct this with a classical convex optimization scheme. We have ground truth data, and now it would be really interesting to apply learned models in such a context to discover the underlying physical effects of observed data. And I think there's also a lot of potential here. Yeah, now to conclude my talk a bit, I want to show the following quote from Thor Heyerdahl, a famous explorer from Norway, who said about borders that he traveled the world quite a bit. He actually never saw one, only hearing that they exist in the minds of people. I think that rings true at the moment. It's of course even more important for humans on this planet, but it's also very important in this context of deep learning. So if we imagine we have the realm of learning methods, and on the other side, the realm of physical systems, there's no way to have borders between those or artificial obstacles or so. The information in terms of data, gradients, all kinds of derivative needs to flow freely, and ideally we should think of these as one unit. There's no reason to introduce artificial borders between these two sides, and I think both sides can profit a lot from very closely working together. And yeah, that's ultimately, of course, also really the bigger picture here. So how can we leverage deep learning techniques and all the powerful simulation methods, take the best of both worlds to improve, ultimately, of course, our understanding and how we can interact with our environment. That is really the larger goal here. And I think there's a lot of very interesting research left in this area. I hope I was able to give you a glimpse of what's possible here. So with that, thanks for listening. All the code of this differentiable flow solver is actually online. Please follow the link if you're interested. Thanks again to all the collaborators, ERC and Intel for funding. And please contact us if any questions should arise. Bye.